Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to discuss the lecture number 9, and the title of this lecture is Data Transfer, Add and Subtract Instructions. Now during this lecture the main topic or main focus will be about the data transfer instructions, especially the MOV instructions and its variants, and add and subtract and how they affect the flex. Before starting this lecture, we will discuss we will review. Before starting this lecture, we will review the previous lecture, what we did in the previous lecture. We discussed about the basic elements of the assembly language, and those elements include integer constants, integer expressions, character and string constants, reserved words and identifier, how we can form reserved words, how we can form identifiers, what are the rules to form an identifier, what are the directives and instructions, what are labels, mnemonic and operands, and how we can include comments. For example, in the integer constants, we saw that how we can define the word constant like integer, and what are the prefixes, like if we want to have the hexadecimal number, then we can have H. For decimal, we can have D, and so on. How we can define these integer constants. And then we defined expressions. For the character strings, we can use quotation mark, single or double quotation marks, and so on. For the reserved words and identifiers, there were some rules that we set, that either the reserved word can start with some special characters like ampersand, underscore, and all these characters. And the directives and instructions, what are the directives, like we use include directive and other directives. These directives were for the assembler to direct the assembler what to do. They are not part of the instruction set or the possible number of instructions which a processor can support, so these directives are not part of those instructions. Then we discuss about the labels. We can use labels. These labels identify the addresses where these instructions are being stored. For example, we can take one example. So there is one label and instruction, and there are some comments. We use comments here. So this label identifies that where this instruction is stored. So actually it is the address of the instruction. Then we discuss about the mnemonics and operands that we can use, and comments like mnemonics like add, subtract, and all these move. These were the mnemonics, and operands can be constants, these integer or other character constants. They can be registers, and so on. And comments, we can use comments in our assembly program, like single line and multi-line comments. For single line comment, we use semicolon sign, and we start and writing the comment. If we want to use multi-line comment, then we have to write keyword comment, and then we have some starting symbol and the ending symbol. So these two symbols must be same, and the comments go, multi-line comments goes here. Then we set up Visual C++, either the Express edition or the Professional edition, how we can set up this Visual Studio to program assembly language inside this Visual Studio. Actually assembly or Microsoft's macro assembler or MASM is maintained, it was maintained by the Microsoft, and now it is integral part of the Visual C++ or the Visual Studio and so on. So we don't need to install separately, but if you want to install the other include file or include directives or the other features, then MASM 32, we also install the MASM 32, and we saw that there are some include files. We set the path, we use this path and C drive to include. There was some includes directory, and then we use this directory, set up this directory inside the Visual C++, and also we did some basic examples. What is a program structure, how we can invoke, we saw how we can monitor these registers, how we can compile, debug, and step-by-step execution so that we can observe the values of registers. Then add subtract example, and this is the skeleton or the structure, basic structure of the program. There's model, then there are some include, preprocessor directives or processor, the assembler directives. Then we have these data and code keywords directives for the assembler. Then here goes the main program where you execute that program. After that, there's in data section we can assign different variables or different identifiers that we can use inside the main program. So this is the basic structure that we use, that we will use in the forthcoming lectures, and also in previous lecture we also use the same structure. So in this lecture we will discuss the following topics: data transfer instructions. There are different data transfer instructions. First of all, we will discuss what are the operand types. We already discussed, so we will review the operand types here. Then we will discuss about the instruction operand notation, how we can define operands inside the instruction, then direct memory operands, then MOV instruction. We already discussed about some examples of MOV instruction. Now we will extensively monitor or extensively discuss this MOV instruction. Then zero and sign extension of this data transfer instruction, how we can extend zero and sign. Then exchange instruction and direct offset instruction. After that we will discuss addition and subtraction instruction, and we will see how these flags are being altered, are being affected by these add and subtract instruction. So आज के दिन इस लेक्चर में हम जो टॉपिक्स डिस्कस करेंगे वो सारी डेटा ट्रांसफर इंस्ट्रक्शन होंगी कि हम किस तरह डेटा ट्रांसफर कर सकते हैं फ्रॉम वन रजिस्टर टू अनदर रजिस्टर, फ्रॉम मेमोरी टू रजिस्टर एंड सो ऑन. उसमें ऑपरेंड्स किस तरह इस्तेमाल करेंगे. उसके अलावा एडिशन एंड सब्ट्रैक्शन जब हम परफॉर्म करेंगे तो कौन कौन से फ्लैग्स, आइदर कैरी फ्लैग, साइन फ्लैग, ऑक्सिलरी कैरी फ्लैग, जीरो फ्लैग एंड सो ऑन, ये सारे फ्लैग्स किस तरह अफेक्ट होंगे या कौन कौन से इंस्ट्रक्शन किस वक्त इनको अफेक्ट करेगी. Inside the data instructions or data transfer instructions, these are the topics. We already mentioned these topics. Now we will observe or discuss these topics in more detail. So what are the operand types? There are three main categories of operand types: immediate, register, and memory. So these are the three main operand types that we will use inside the instruction. We already discussed that what are these, how we can use these operands, but now we will see how we can use them inside the instruction in assembly language. So immediate operand type, these are the basic operand types. Immediate operand type क्या होती है? It is a constant integer. ये constant integer होता है. ये या तो 8 बिट का होगा, 16 बिट का होगा, 32 बिट्स का होगा. कांस्टेंट इंटीजर भी हो सकता है, और इसके अलावा ये कोई और वैल्यू हो सकता है हमारे पास. सॉरी, मैं इसको मिटा देता हूँ. या ये कोई एड्रेस हो सकती है, या कोई ऑफसेट हो सकता है, व्हाटसएवर. सो द इमीडिएट ऑपरेंड कैन बी, जो पहला बेसिक ऑपरेंड है वो है इमीडिएट. इमीडिएट इज अ कांस्टेंट इंटीजर. दिस कांस्टेंट इंटीजर कैन बी 8 बिट्स और 16 बिट्स और 32 बिट्स. अब इसमें जो हम इंटीजर वैल्यू डिफाइन करेंगे वो या तो 8 बिट का होगा, 16 बिट का, या 32 बिट्स का होगा. सो दिस वैल्यू इज इनकोडेड विद इन द इंस्ट्रक्शन. हम ये वैल्यू इंस्ट्रक्शन जब राइट करेंगे तो उसके अंदर ही लिखेंगे. जिस तरह हम लिखते हैं मूव aid or something, in instructions के अंदर हम ये operand लिखेंगे directly. The next operand or basic operand type is register. This register operand type is the name of register. So these register can be 8-bit, 16-bit, 32-bit or 64 bits. Right now we are considering 32 bits, so we will use the EAX, EBX, ECX and so on, all these 32-bit notations. You already know that we discuss about what are the naming notations for 8-bit, 16-bit and 32-bit registers. So we will use these registers inside the instructions, and during the last lecture you saw that we had used EAX or EBX and so on. We used also in the move or add or subtract instructions. So now this is the another type of basic operand that we will use. Third one is the memory. We will refer any location inside the memory. So this memory location or memory address is encoded within the instruction or a register that holds the address of the memory. या तो हम कोई भी एड्रेस लिखेंगे इंस्ट्रक्शन में, या उसके साथ उसके अलावा हम कोई भी रजिस्टर लिखेंगे, वो रजिस्टर जिसके अंदर मेमोरी लोकेशन स्टोर होगी. Now we'll see how we can refer them. So these are the three basic types. हम इन तीनों बेसिक टाइप्स को एक्सप्लोर करेंगे ड्यूरिंग दिस होल कोर्स of assembly language, and we will experimentally see them how we can use this one. So these are the instruction operand notation. When you will discuss when you will study the manuals, जब भी आप assembly language पढ़ें तो उसके लिए Microsoft में या कुछ अदर जो है आर्किटेक्चर्स ने अपने माइक्रो प्रोसेसर के लिए स्पेशली पूरा का पूरा मैनुअल बनाया होता है इंस्ट्रक्शन सेट का. वो मैनुअल इस्तेमाल होता है to program those microprocessors. Similarly, Intel has the complete list, and also the Microsoft has provided the same list which you can use. But for the if you want to know the complete information, what are the instructions, how they are using the operands and so on, so you will find these notations inside those manuals, or these notations whenever we study the in-depth information about the operands inside the instructions. So these are the notations. When we say R8, it means it's an 8-bit register. It's 8-bit general purpose register like AH, AL, BH, BL, CH, CL and DH, DL. These are these A, B, C, D. These are the 4 general purpose registers. Their notations are different, but we will see. So for 8-bit it will be AH, AL, BH, BL and CH and so on. जब हम कहते हैं कि 16-bit register, it will be shown as R16. R16 ये 16-bit register की नोट को शो करता है किसी भी इंस्ट्रक्शन सेट में, और इंस्ट्रक्शन सेट के मैनुअल में और उसके जो साइन टेक्स्ट हम लिखते हैं उसमें. सो इस 16-bit जनरल पर्पस रजिस्टर को शो करने के लिए हम R16 यूज करते हैं, एंड दीज रजिस्टर्स कैन बी AX, BX, CX, DX, source index, destination index, stack pointer, base pointer and so on. Then R32, definitely it is evident from the name that this is the general purpose register, but 32-bit general purpose register, and these 32-bit can be EAX, EBX and so on. Register, when we say register, it can be any. When it is written that move, for example, if we know this, if we want to consider the example of move instruction, so if it is move, and then if I say R8 comma R8, it means here we consider general purpose register, 8-bit general purpose register and so on. So this is the syntax of move instruction. Here or sometimes it is written R8, R16, or sometimes they write register only. It means it can be any register here or any register here. So these are the notations operand notations that are being used for the registers. Then S register, if it is S register, then these are called the segment registers. But S register is 16-bit register, is considered as a 16-bit register for CS, DS, SS, ES, FS and GS. So we have code segment, data segment, stack segment and so on. Similarly, if we have immediate value, in case of immediate operation mode or immediate access, immediate memory access. So in this mode we will use the immediate value, and these immediate values can be 8-bit, 16-bit or 32-bit until and unless they are specifically mentioned, like here immediate 8, immediate 16 and immediate 32. So they show either the 16, 8, 16 or 32-bit respectively. Now here, when the notation is written like this one, all these three notations, so R/M8, R/M16, R/M32, obviously you can note that R shows the register, R here, M shows the memory, M shows memory and R shows the register. So it means if somewhere in the manual, if it is written R/M8, it means the operand can be 8-bit operand, and that can be a general purpose register or it can be a memory byte. And similarly, RM16, it can be a 16-bit operand, which can be a 16-bit general purpose register or 16-bit memory word, or sorry, the memory word. And 32-bit, it can be a double memory word or double word, or it can be a 32-bit register. Otherwise, next, if it is mem only, it means we just refer the memory operand, or we refer memory location or memory. It can be 8-bit, 16 or 32-bit register. Now we will discuss about the direct memory operands. डायरेक्ट मेमोरी ऑपरेंड्स में हम डिस्कस करेंगे कि जो ऑपरेंड्स हैं, हाउ वी कैन रेफर मेमोरी लोकेशंस डायरेक्टली. आई विल जस्ट रिमूव दिस वन. अब हम डिस्कस करेंगे कि मेमोरी को हम डायरेक्टली किस तरह एक्सेस कर सकते हैं, हाउ वी कैन यूज डायरेक्ट मेमोरी लोकेशन inside our instruction. So a direct memory operand is a named reference to storage inside the memory. So whatsoever you define in data section or data, it is stored inside the memory. If it is a byte, for example, you can consider this is a byte. It means here are addresses, address, and this is data for part. So 10 hexadecimal is stored here, 10 hexadecimal, and this is the memory location 0xF100 or whatsoever the memory location. So now actually this is the offset. When we refer, then this variable 1 is the offset and so on. So we will use, or automatically it will be used with the segment register or displacement with the segment register and so on. So this, the named reference or label is automatically dereferenced by the assembler. How we can see? For example, we defined variable 1. Definitely this variable 1 is representing the memory location. Variable 1 represents the memory location inside the data part or data segment. So how we can refer it? If I write move AL and variable 1, so what will happen? The value, whatsoever the value that is being stored or that is stored inside the that location, either it is byte, word, double word, it will be transferred to the destination. Now depends, if you want to transfer 16-bit to 16-bit, 32-bit to 32-bit, source to destinations relationship. Just we will discuss what will happen if you convert or if you transfer or if you move 8-bit to 16-bit or how you can move 8-bit to 16-bit, 8-bit to 32-bit, 16-bit to 16-bit, or 16-bit to 32 bits, and so on. What will be the consequences, how we can perform that one. We will see experimentally how we can do that one. So this is the alternate format. This is the alternate format you can write. So this will show the memory location. So we are referring here the memory location, and memory location whatsoever the value is at that memory location, it will be transferred to the AL. So here you can see variable 1 is byte, means 8 bits, and AL is the lower order byte of the AX register. AX register has two parts, AH higher order byte and AL lower order byte of the accumulator. So this we are going to transfer byte or 8 bits to 8 bits. So the new values or the value of this AL will be 10 in both the examples. So the latter one is the alternate format you can use. Now the move instruction, we have seen move instruction so many times. So we have used this instruction. हमने move instruction को पहले भी इस्तेमाल कर चुके हैं इसको. अब इसको देखेंगे कि इसके alternative formats क्या हो सकते हैं. Move instruction, its main purpose is to move source data to the destination, or source data from the source operand to the destination operand. So this is the syntax. We already saw that syntax in the previous in few previous slides, few previous presentations. Now this is no more than one memory operand permitted. It's only one memory operand permitted. You cannot use multiple memory operands to be used inside the move instruction. So just be careful. You cannot move whole complete array into multiple operands. No, only one memory operand can be as a destination. And other thing, code segment. Just remember, code segment, EIP, or instruction pointer, 32 bits, 32-bit instruction pointer, and the instruction pointer 16-bit. They cannot be used as a destination registers. So these code segment, EIP, or instruction pointer in 16 or 32 bits, they cannot be used as the destination registers. So just keep these segment registered. Avoid to use these segment register. They are not permitted to be used inside because instruction pointer is only used by the microprocessor when it controls the execution of the program. So this you cannot use that, you cannot alter that one inside the program. And no immediate to segment moves. No immediate to segment moves. You cannot transfer any immediate value, means whatsoever the integer constant is there, either it shows any value or something, you cannot move. आप उसको move नहीं कर सकते किसी भी segment register में. So just try to avoid, otherwise you will get error. आपको error मिलेगा. Here you can see the example, very basic example. The example is that we defined two variables, two operands we have defined. One is called count variable or count, and one is called WL, or WL is the name. So count is only byte size, and WL is the word size. Their values are 100 and 2. So 100 until unless it is defined, otherwise it is like the considered as a integer value. So right now we did not define h here. What will happen if we define 100h? I will answer this question later on. What will happen if we define the 100h? Here it is decimal. Until and unless means either we define D or not. In D or not, if there is no notation here, it means it is decimal. Definitely it is decimal. Now inside the core segment there are three different sets of instructions. Move BL. move BL. So this is the lower order byte of the B register, like BH and BL. So BX register has two parts, BH and BL. So this is the lower order byte of BL register, B register. So this is 8-bit long. It can hold 8-bit information. Now what we will do, what we are going to do here, we want to transfer 8-bit data, or we want to move 8-bit data to BL lower order byte and B register. So it is okay, it is permitted. Here you can see AX is 16-bit register, and word is also 16-bit. So we want to transfer 16-bit value to 16-bit. Destination and source, their size is same. Their size is similar. So what we have to do, we have to transfer or move data between two similar source and destination, two similar operands. Count is a location, and AL is the operand, the lower order byte register, so of the accumulator register. So what we are trying here, we want to move contents of AL register, whatsoever the value is inside that register, we want to move inside the count or at the memory location, which is represented by the count. Here is another set of these instructions. I will just erase all this. Here is another set of instructions. This set of instructions, you can see here, is a move AL comma W well. So AL comma W well, there's one problem here with the AL comma W well. What is the problem? The size of this W well is size of this W well is 16 bits, and size of AL is 8 bits. So it doesn't match. So you will get error. Here you can see you will get error. Now the next is AX, and count is 8 bits. Count is 8-bit wide or 8-bit long, and AX is 16-bit. So you will also get the error. Here this is the 32-bit register, and you are trying to move count, which is the 1 byte. So even then you will also get the error. Now this is the drill or practice. What we are going to do here, for example, explain why each of the following move statements are invalid. Why these, here you can see these are invalid. What is the reason? What is the reason that these are invalid? Where we have defined, just see here, look at this one. Well, B well is a register. This is register 1, this is the variable 1 which we defined here, B well. It is 1 byte or 8-bit. This is 8-bit, but there is no value. Value is undefined. Value is not declared, right? Value is not assigned here. So, and there are two other variables, W well and D well. So this is the word and double word, and their values are already defined. These are decimal values 2 and 5. The reason how we cannot, what is the reason that following statements are invalid? Following statements or following instructions are invalid. Just think, what is the reason? Here first instruction is DS, then ESI, EIP 25, B well 2, comma B well. B well 2, comma B well. What is the reason? First one is immediate move to DS is not permitted. As we discussed in the previous slide, you cannot move immediate value to the data segment or segment registers. ESI, there's a mismatch in the size, because ESI and WWEIGHT, source index, and WWEL. WWEL is the 16-bit, and ESI is 32-bit. So you cannot send this move this value of dval to the ESI, sorry. And for the ESI, for the EIP cannot be the destination, as we discussed in instruction pointer cannot be the destination. It's not possible. So instruction pointer is not possible to be a destination. And then immediate value, here you can see this is a constant value 25. This constant value doesn't represent any identifier. If we have used any identifier, then it must be defined here. This cannot be any identifier. So immediate value, it cannot be a destination. Immediate value cannot be a destination. Destination can be a valid register or a valid memory location where we are transferring the value. The last one is memory to memory move. It's not permitted. You cannot copy from move from memory to memory. So it's not possible. Even though their size is same, you can see bval and bval2. Their size is similar, but these two represent the memory locations or memory, the 2 bytes inside the memory. So memory to memory location or movement is not permitted. So this was all about this slide, and then we are going to move. Now here you can see 0 extension, move with the 0 extension. You can copy a smaller value into a larger destination. Now here, what is the alternate if you want to copy, if there is a size mismatch and your value is less than the destination operand value that you want to transfer, our source operand value, our source operand size is less than the destination operand size, then what we can do, हम क्या कर सकते हैं, हम उसका वैल्यू को एक्सटेंड कर लेते हैं, उसकी साइज को एक्सटेंड कर लेते हैं. साइज को एक्सटेंड करने के मल्टीपल तरीके होते हैं. एक होता है साइन एक्सटेंशन, दूसरा होता है जीरो एक्सटेंशन. ठीक है, इनमें डिफरेंस क्या होगा, वी विल डिस्कस. सो फर्स्ट इंस्ट्रक्शन और फर्स्ट वे is we can extend by putting or by filling all zeros in the higher order bits, जो हम उसमें नए bits add कर रहे हैं. जिस तरह आप इसमें slide में देख सकते हैं कि this is the source operand here. So we have source operand, and what we are going to do, we are going to fill here all these zeros. I want to change the color so that you can see. So we want to fill all the zeros at this point. Here we want to fill all the zeros, and then we will transfer them, or we will transfer or move this value to the destination. So destination, whatever the destination is there, we will move inside this destination. The instruction that we can use here, the instructions that we will use, so I want to change the in color because I cannot see the white. So the instructions like move BL, if I write move BL, it's okay. If I write move BL and this one is, so BL is 8-bit long and this value is also 8-bit long, it's in binary, so it's 8-bit, and BL is also 8-bit. So I want to move 8-bit to 8-bit, it's okay, we can move that one. So if I want to move BL to the AX, BL is 8-bit and AX is 16-bit. So what I will do, the another instruction is called the move ZX or 0 extended. Move 0 extension. Move with the 0 extension. So this value 1000 and 1111, this binary value will be extended with 0, and this value will be transferred to the AX. Now in the next slide, the sign extension. This is another way to say or to move lower or mean this source operand which is less or whose size is not equal to the destination operand. So what we have to do, first we saw that 0 extension, then we have the sign extension. Now what will happen in the sign extension? In the sign extension will not fill zeros in the extension part or higher order bits that are being added. इसमें आप देख सकते हैं साइन एक्सटेंशन और जीरो एक्सटेंशन में क्या था, हमने इस सेक्शन में सारे के सारे जीरोस फिल कर दिए थे. ये जो सेक्शन था, ये साइड था, इसमें सारे के सारे जीरोस फिल कर दिए थे. उन जीरोस को फिल करने से ये इफेक्ट होगा कि अगर आपका वैल्यू नेगेटिव वैल्यू है देन इट विल बिकम पॉजिटिव वैल्यू, बिकॉज ये 1 जो था, फॉर एग्जाम्पल यहाँ पे ये जो 8 बिट वैल्यू है, if you consider it as a sign value or sign byte, then this must be a negative value, because this one shows the negative sign. 8th bit or the most significant bit shows the signed value in this 1 byte location or 1 byte representation, so this must be a negative value. But if you add zeros here, then definitely in 16-bit representation this will be the sign bit. Here in 8-bit this will be the sign bit. For this signed byte, whole or signed value, this most significant bit, 8th bit or bit from 0 to 7th bit, so most significant bit shows the sign, and in the 16-bit value this will show the sign, or this most significant bit will show the sign. So in zero extension, sign can be affected. For the negative value, it will become positive value. It will become wrong positive value, so its sign will be affected. Even it will not be the same value in positive, but its sign will be affected. But in sign extension, the sign bit, whatsoever the sign bit is, if it is like 1, ones will be filled for the most significant byte or whatsoever there is you are extending. If you are extending from 8 to 16 bit or 8 to 32 bits, then 3 bytes will be extended. If you want to extend 1 byte to 4 byte, the 4 byte like 32 bits, or if you want to move 1 byte to 16 bit, then 1 byte will be added. So here we want to move 8 bit information towards the 16 bit information, so this 1 byte is added. It's already, this one is 1 byte, so we add 1 byte, but we will add all these ones. In case if this value is like 0 0 0 0 and 1 1 1 1, and the sign extension it will be 0 0 0, 8 zeros here, 1 byte. So this value will be moved or transferred towards the destination operand. So it will not affect the value. It will not affect the value. It will only extend the value, not extend the value, extend the representation of that value from 8 bit to 16 or 8 bit to 32 bits and so on. So the upper half of the destination will copy the source operand's sign bit, and here you can see the example. If it is 1 0 0 0 and 1 1 b, so move sign extended. It previous was 0 extended. Move 0 extended previous slide, and this is move sign extension. So be careful whenever you program, and if you want to perform movement between two operands whose size mismatch, then what you have to do, you have to apply any of these two operands or operations to perform movement from source to destination when their size mismatch. So आपने बहुत ही ध्यान से इस्तेमाल करने, otherwise you will get errors. You must be very much careful. Now we will move towards the, so the destination must be a register, okay? Otherwise you will get error. There is the exchange instruction. Now the exchange, as it is clear from its name, or XCHG, are called the exchange instruction. So this exchange instruction exchanges the values of two operands two operands, the values will be moved or exchanged. So not moved, but their values will be exchanged. It will not move source to destination, but it will exchange the value of two operands. Value of one operand will be saved to the another operand, and another second operand's value will be transferred to the first operand. So here you can see at this point the exchange the values of two operands. At least one operand must be a register. One operand must be a register. Another operand can be a memory location. So one operator can be a register, and another operand can be a memory location whatsoever. So register and memory whatsoever. Here in this example you will see. Now one thing, you cannot use immediate operand, because immediate is a constant. Immediate operand or immediate value is a constant value. So you cannot use constant, because we need somewhere to store information. For example, if you will see here, we have defined two variables. Variable 1 is the memory location, and it's of size word, means 16 bits, and here variable 2 is a word size, 16 bits. Their values are in hexadecimal. And at this point, the code, inside the code you can see there are 3 instructions or 4 instructions: exchange, AX, BX, AH, AL, variable 1, BX, EX, and EBX. Now you can see 16-bit to 16-bit exchange, 16-bit to 16-bit, lower 8-bit to 8-bit exchange. Variable 1 is 16 bits, BX is 16 bits, EAX and EBX 32 bits. So you can see 16-bit register transfer or exchange, 8-bit register exchange, and register to memory exchange, and 32-bit register exchange. Here variable and there are two memory locations. As we saw in our move instruction, you cannot perform move between two memory locations. From one memory location you cannot move towards the another memory location. Same thing happens here. यहाँ पे भी वही चीज़ होगी. आप मेमोरी से डेटा लेके मेमोरी में ट्रांसफर नहीं कर सकते डायरेक्टली विद इन वन इंस्ट्रक्शन. You can perform, but some other techniques, not by move instruction or exchange instruction directly. जिस तरह आप move instruction में एक memory operand जो है लेके या एक memory location से डेटा लेके दूसरी memory location पे सेव नहीं कर सकते by using move instruction. इसी तरह exchange instruction में भी ये होगा कि आप एक मेमोरी लोकेशन से डेटा लेके दूसरी पे रखें और उस दूसरी सेकंड लोकेशन से लेके पहली लोकेशन पे रखें. इट्स नॉट पॉसिबल. सो एक्सचेंज एंड मूव बिटवीन टू मेमोरी लोकेशंस इज नॉट पॉसिबल. इट्स नॉट पॉसिबल, नहीं हो सकता. सो यू विल गेट एरर हियर इफ यू वांट टू परफॉर्म मूव बिटवीन टू मेमोरी ऑपरेंड्स. सो नाउ वी कैन मूव this is called the direct offset operand. Direct offset operand. Here a constant offset is added to a data label. For example, here is the data label, and this data label is a byte. This is 4 byte and 4 byte, and this one is the array. This one is the array. Memory arrays in memory are shown like this one. For example, if memory is increasing in this direction, then we can use like this one, 10 or 20, 30 and 40. So I can write here so it can be either 10, 20, 30 and 40. This is the 1 byte array. It's not 1 byte array, its element size is 1 byte. So here you can see inside the code what we are going to do. We are we're adding a constant offset. We are adding, so here in the data section, here is the data section, continuous data section. So what we are going to do, we are going to add constant offset or direct offset. So what will happen, the address is dereferenced to get the value inside its memory location. So we will, an effective address will be calculated. Data label and the offset, they are combined or added to calculate the effect address. So how it will happen, for example, array shows the starting address, either this one or this one, whatsoever the increasing direction is, and array like this address is to F200, F201, F202 and F203. Similarly, this one will be F200, F201, F202 and F203. These are the addresses. Now the array B or byte array, so its name is array B, shows the starting location. Array B shows the starting location. What will happen if I write array B plus 1? So this is the direct offset which we add, and the value, so B shows this value, this address. If we add 1, what will happen, it will add 1 with the F200, so it will be F201. So this value will be transferred to the AL. And this is the alternative notation. You can use these angle brackets. So this will also reference the same memory location. So array B, its memory location is F200 and plus 1. So it will add the 1 inside that address, which is being shown by which is being represented by the array B identifier. So here you can see. So why doesn't array B produce the result like 10 plus 1 or 11H? Because we are going to refer the addresses. Array B doesn't show or doesn't represent all these values, or it is not like the indexes inside the C or C++ or other languages. So even in other languages, name of the array represents the memory location. Okay, so direct offset, we can also use the constant offset. We can use the same constant offset here. You can see the word or a double word. Now there is difference in this direct offset if you use word or double word. So in case of word or double word, how data is represented inside the memory. For example, this is the memory, same example, the previous example. Now first memory location, I will use dots, then another memory location, then dots. So if there are 3 elements, what will happen, this 100H is a word size, or if it is in case of double word size, then it must be represented with by the 4 bytes. But here we take the case of word, so it is 2 byte long or 16 bits. So 1000 hexadecimal will occupy 2 memory addresses. For example, F200 and F201. So these 2 bytes are store this one word data, and then F202, F203, these 2 bytes show the 200 hexadecimal. Similarly, F204 and F205 show the how can we say, the 300 in hexadecimal. Now what will happen if we refer, so this is the starting location, it is shown by the array W. Array W is the name of this or label for this memory location or name of the array. What will happen, so this data label or array name shows the starting address. If I write array W plus 2, it means it already shows the F200. If I add F200, if I add 02 or only 2, it will be F202. So whatsoever the starting location is, whatsoever this location is, it will give you the, it will transfer these 2 bytes or 16 bits inside the AX, inside the AX. Similar case is for here. For AX, I want to transfer the byte. So here you can see this, at this memory location, these 2 bytes, ये जो 16 bits का value है वो transfer होगा AX में. If I add 4, then definitely whatsoever the word stored at the starting location F204, it will be transferred to the AX. Now here, if I write array D, now here is this is the example for the double word. So the same case goes for the double word. If I want to store these 1000, 100, 200 and 300 hexadecimal. So now we will consider the case for the 32-bit case like array D. So array D, for example, starts with the memory location F200 and it will continue from F200 to 4 bytes, F20100 to 03 second. So value here is whatsoever the value is, the 32-bit value, number of zeros, and 1 will be here, and 2 will be here, and 3 will be here. It will be appended with the zeros, all the zeros, and so on. So if we use this instruction, array D plus 4, so what is, suppose array D shows the or represent the address, starting address is F200, 4 will be added. So whatsoever the word or double word is here, it will be transferred to the 32-bit accumulator. So in this slide we will see how we can this main objective is to exchange, to use exchange and move instruction to arrange the arrays or array value into this order, like this order. Right now the order of this array is like same, like first element is 1, second element is 2, third element is 3. So we want to rearrange them into this order, like 3, 1 and 2. Initially what we will do, the first step, this is our desired format or form. This is our desired form and this is the current form. What we have to do, first thing, we have to copy the first element, EAX is equal to 1 right now here. So EAX is equal to 1. Copy the first value into EAX and exchange it with the second value. How you can do that one? So array D, the first element will be moved towards the EAX. So we have moved EAX with the 1, and then we can perform exchange with the second one. So exchange with the second one, how we can exchange? Initially the value inside the array is like right now is 1, 2 and 3. So we want to exchange with the second one. What will happen? That now the new array and the new value of EAX, so EAX new value will be 2, and inside the array it will be 1, 1 and 3. So we have exchanged the value of the second element of this array and the EAX. So 1 and 2 has been exchanged. Next step is exchange EAX with the third value. Exchange EAX with the third value. So currently EAX is equal to EAX is equal to, and current position is this one. So how we can perform? We can use exchange with the third. So after performing exchange, new value of EAX will be equal to 3, and the current values will be, so we perform exchange EAX with the third value. So 1, 1 and 2. So 3 is in the EAX. Now the second value is second operation is move EAX is at the first place. So after this one, EAX value, EAX is equal to 3, and we are going to perform move only. So move doesn't change the contents of EAX. 3, 1 and 2. This is the desired format here by using the exchange and all this. Here you can see another example. So if we want to write a program that aids the following 3 bytes, we want to add these 3 bytes. So how we can add these 3 bytes? First thing is move AL with the M byte. So this is the array. We want to move AL with the M bytes, and whatever the M bytes are. So for example, if we do this one, so this value will be transferred in the AL. Similarly, add AL with the M bytes plus 1, then add AL, because this is the byte, this is the byte. But is this code valid or not? We are just going to perform 8-bit addition. 8-bit addition. We just move AL and perform this addition. Is this valid or no? The answer is this valid, is the new code or this code is valid or not? For example, here you can see M bytes is 1 byte, and AX is 16-bit or 2 bytes. Here is 16-bit. What's your idea about this code? Is it possible? What about this one? What about this one? If I want to perform move 0x, my bytes are the first byte into the AX with the 0 extension, and then what I perform move BL, this one, then BX and AX, perform addition, move BL and my bytes, second and the third element, and perform addition. X is equal sum. Is there anything missing here? Is there anything missing? What is missing inside this one? Now, one thing that is most common which is missing is, first we have to move zeros to BX. We don't know that either what is the value inside the higher order byte of the BX, because BX is combination of 2 BH and BL. What we are going to do, we don't know what is the previous value inside BL, but we are only moving value in the BL, and we are performing addition by using complete BX. So the best thing is you can do that one. So what we have to do, but one thing, if you are using the signed one, then don't use 0 extension. Use move sign extension. Don't use 0 extension. So these are the 2 instructions. But before going to perform this type of addition, what you have to do, you have to perform the assign zeros to the higher order byte, to the complete BX, move zeros to complete BX, and then assign or move any value in the lower order byte, and then perform addition. So addition in subtraction, we have increment and decrement instruction, add and subtract instruction, negate instruction, implementing arithmetic expressions, flags affected by the arithmetic. What are these flags that will be affected? We will monitor, or we will analyze these one. So if we want to perform addition and subtraction, these are the instructions or the operations that we will discuss right now. Add 1, subtract 1 from destination operand. So add 1, subtract from the destination operand. We can use increment or decrement. So increment and decrement instruction, what they do, ये दोनों instructions जो destination operand है उसमें से एक माइनस करती हैं या एक प्लस करती हैं, डिपेंड्स ऑन दी ऑपरेशन. अगर हम इंक्रीमेंट लिखेंगे तो उसमें 1 ऐड कर लेगी, अगर डिक्रीमेंट लिखेंगे तो उसमें से 1 माइनस कर देगी. उसके बाद ये हम एग्जांपल डिस्कस करेंगे. इनसाइड दिस एग्जांपल वी विल सी व्हाट इज गोइंग टू हैपन कि वी डिफाइन माय वर्ड word is 100 in hexadecimal, and my double word is all these 1 and all these zeros in hexadecimal. So 32-bit and 16-bit. We define two operands. Now we want to increment word, so we write increment my word, decrement my word, increment my double word. So this is okay. If I say move 00F in AX, and if I want to increment, it will become 0100, because I will add 1 here, so it will be 100, 0100 after performing increment AX. If I move 00FF in AX, and if I say increment AL, if I say increment AL only, so what will happen? We are just going to increment AL, but if AL is value inside the AL is FF, if we increment, so the carry will be discarded. Carry will be discarded and the value will be 00. So the new value for AX will be, new value for the AX will be 000 and so on. Here we are performing increment on 16-bit register. Here we are performing on the lower order byte of the accumulator or AL register. Now what will happen if you do that one? So that will be the result. So to perform increment and decrement, you must have to be careful on which operation is being performed on which part of the register or which complete register. It will affect the results. So you have to evaluate data. The byte is 0, FF and 0. There are two values, my byte, and there are two values. So if I write move AL, so what should be the value in the destination? If I write move AL, my byte, move AH, my byte plus 1, decrement AH, increment AL, decrement AX. Here AL is moved with the byte, my byte. If we execute all these instructions, what will be the values of AL, AH and AX if we move or execute all these instructions? Just think. So the destination operands are AL, AH and AX. We execute. The values will be FF 00, FF 00, FE and FF. Why and how? Because my byte, its value is 0, FF 0FF. We use 0 here because the starting digit of this hexadecimal is F or a character. So that's the reason we write 0 here. It doesn't mean this is like 12-bit hexadecimal value. No, we use 0 before any number in hexadecimal if it starts with any letter. So what will happen? We use 0. So we are going to move FF into the AL. So AL will be equal to FF. If we say move AH with byte plus 1, so second element, AH will be moved with the 00. And decrement AH, we want to decrement AH. So if we decrement AH, so if we subtract 1 from AH, its value will be FF, or in the how can I say, the it will be FF. This is decrement. We can have minus value or you can have FF. If we increment AL, so if we increment AL, definitely already value of AL is FF, and if we add 1, it will be 0, 0 and 1 will be discarded. It will be as a carry, so it will be discarded. So what will happen? So for example, it will be 15 plus 16 is equal like 10. So we will put 10 in hexadecimal. So what we will do, we will take this 1 here and then with 10, so 0 will be here, 1 will be carry. This is not 10 in binary, it is in hexadecimal. So what will happen, we will discard the carry and the value of AL will again be 0, 0. If we decrement AX, now what will happen? You see here, actually we are performing decrement AH. So if we decrement AH, it will be, here it will be, it's FF, and decrement AL, it will be 0 0, and if we say decrement AX, then its value will be like this one. So currently the value of AL is equal 0 0. So this one is F, not the E. So its value is F, not the E. So because it will be F F F F. So if we decrement, then it will be here it will be F F and F, all these F F and so on. Add and subtract instructions. So add instruction is used. There are two operands which are being used. So what it will do, it will add the destination, add the source with the destination, and again store result inside the destination. Now here the same case goes for the subtract instruction. Source is added with the destination, and the result is again stored to the destination. So source is subtracted from the destination and added, the result is transferred to the destination. And the same operand goes for the same operand rules as for the move instruction. Like first we first perform and then move towards the destination. For example, the values for EAX, if we have variable 1 and variable 2, for example, variable 1 value is transferred to the EAX. They are double word, so 32 bits, so it should be EAX. Variable 2, its value is being moved or added with the EAX. So if we add the value of EAX, previously the value of EAX was equal to 1 0 0 and 0. Now we add, now what we do, we add variable 2 is 2 0 0, so it is being added here. It will be the new value of EX will be 3 0 0, and add AX with this one. This is the immediate value for AX. So this value will remain same, only the AX value or 16-bit value will change. That is the reason I mentioned in the previous slide. If you want to use change any part, or you want to use complete register, so be careful when you apply those operations. So here you can see add EAX 1, so we add 1, so it will be 4 0 0, and subtract AX 1, so it will be 0 0, and FFF 4 0 0 0. So we just subtract from this part, not from the complete EAX. So just be careful. Negate instruction, this instruction reverse the sign of an operand. Operand can be register or memory operand, so it will negate. It will reverse the sign. It will not reverse the value or mean the convert into the 2's complement or something. Only reverse the sign. It will reverse the sign. So how it will reverse the sign? Will be. So now we will discuss about the negate instruction. This negate instruction, it reverse the sign. How it will reverse the sign, you can see here. And the operand can be a register or memory location. So memory or register operands can be used. Here are two memory operands, val b and val w. Val b is a memory operand of size byte and its value is -1. दूसरा जो हमारे पास मेमोरी ऑपरेंड है उसका नाम है val w और ये वर्ड साइज है, इसका वैल्यू है +32767. एंड यहाँ पे हमारे पास 3 इंस्ट्रक्शंस हैं, मूव AL कामा val b. सो val b मेमोरी ऑपरेंड में जो भी वैल्यू है वो AL में ट्रांसफर हो जाएगी. अब AL 1 बाइट है, val b इज ऑल्सो 1 बाइट, सो उसमें -1 आ जाएगा. अब हम नेगेट करते हैं AL को. AL में जो भी वैल्यू है उसको हम नेगेट करते हैं. नेगेट करने के बाद क्या होगा, उसकी साइन चेंज हो जाएगी. एंड देन नेक्स्ट इंस्ट्रक्शन जो हमारी है वो है नेगेट val w. सो मेमोरी ऑपरेंड का हम वैल्यू जो है वो नेगेट करते हैं, उसको क्या कर लेते हैं, उसको चेंज कर लेते हैं. प्रीवियसली वो 3276 था पॉजिटिव, नाउ इट विल बी माइनस. And suppose that AX contains -3276 and we apply negate to it, what will be the result? अगर AX में -3276, so now we will discuss about the negate instruction and how does it affect the flags. How does processor implement this negate instruction? So it use negate by the following operation: 0 and operand. Operand is subtracted from 0 minus the operand. 0 minus the operand, and again result is sent to the same operand definitely. So what will happen? So 0 is operand is subtracted from the 0, and any non-zero operand causes the carry flag to be set. Any non-zero operand set this carry flag. For example, if I say val B is byte 1, there are two values here. Val C is sign byte minus 128, and code is negate val B. So if we negate val B, this carry flag will be equal to 1, and the OF flag will be 0, or overflow flag will be 0. Here if we negate val B and the next element, if the next element, so carry flag will be 0 because next element is 0. So if we subtract 0 from 0, so there is nothing, and overflow flag is nothing. If we say negate val C, so we want to negate val C, definitely the carry flag will be 1 because 128 is the minimum value that we have here, and if we negate this one, so the carry flag will be affected, it will be 1, and the overflow will also be 1. So how we can implement arithmetic expressions inside our programs? High-level language compiler, they translate mathematical expressions into assembly language. Definitely, even if you write a plus a is equal to b plus c, for example, in C language or C++, so that high-level language, or the like other Fortran, Pascal, and all these languages, they transfer these expressions into assembly language. How can we do that? For example, RVal is first expression, first operand, and there are 3 other operands on the right side. So minus xval plus yval minus zval. These are the 3 variables that we are going to evaluate and transfer value to the 4th. So RVal is a word, we don't know its value, value is not initialized. Xval, D, and the yval and zval, these are the values that are being assigned. For example, for the xval it will be minus 26 plus y value is equal to 30 minus 40. So if we just subtract, or means perform this operation, what will happen? So we have to evaluate first. So move EAX xval and negate. EAX xval is moved here and is negate. So EAX is minus 26. Move EBX yval. So yval's value will be moved to the EBX, and subtract zval from the EBX. Value is equal to minus 10. So this is minus 10 for this one. And then what we'll have to do, we have to add EBX and EAX. So EAX already has got minus 26, and we add this value for EBX. So the final answer is minus 36. But what we have to do, so EAX is the final answer because this instruction will be performed like this one. So EAX is equal to EAX minus EBX. So EAX was minus 26 minus 10. So again the value, whatsoever the values, it will be transferred. Minus 36 will be transferred into the EAX, and we have to move this value of EAX to the RVal, the memory location. So in this slide there's an exercise how you can perform transfer of this expression into the translate this expression into the assembly language. And we have this xval, yval, and zval. First we have to perform this one, then perform addition, and then subtraction. So first assign to the EBX So EBX is this one we have negated. Then we have to perform EBX and this one the addition. Then what we have to do, we have to perform eval or transfer eval to the EAX, and then we have to perform the subtraction between this one and whatsoever the value we have got this one. So EAX value is transferred to the eval. The flags that are affected by the arithmetic, definitely there are zero flag, sign flag, and carry flag, and overflow flag. These are the most common flags or essential flags. So the ALU has number of status flags. We already know the list of these flags that reflect the outcome of arithmetic and bitwise operations. It is based on the contents of the destination operand, how we just perform these, what are the contents of these two registers and so on. And then these are the essential flags, as I already mentioned: zero flag, sign flag, carry flag, and overflow flag. And move instruction, it will never affect, because move instruction doesn't perform any arithmetic or the bitwise operation. Concept map, we already know we have the bitwise and arithmetic operation. They affect the status flag, and they are being used by the conditional or jump instructions, and they provide branch logic, and ALU executes these instructions, and status flags are attached to the ALU, and ALU is part of CPU, and CPU executes also these, perform these conditional jumps and so on. This is the conceptual map. So you can see that bitwise and arithmetic operands, they affect the status flag, and definitely ALU perform these operations, and ALU is part of CPU, and CPU executes jump instruction. So you can use this diagram such as those to express the relationship between assembly language concepts. Zero flag, we know that zero flag is set when the result of an operand operation produces 0 in the destination operand. So for example, if we move CX with 1, subtract 1 from CX, what will happen? The CX value will be 0. Definitely CX value was 1, and we are subtracting 1 from that 1, so 0 flag will be high. And if we say move AX is equal to 0, F, 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 and F hexadecimal, and if we increment AX, then what will happen? 0 flag will be 1, because AX, these are the 8 bits, and FF is already all these values are like, all these are 1 1 1 in the AX. 16 bits are all ones. If we increment, there will be all zeros, so actual value will be 0. If we increment AX again, then auxiliary carry will be 1 and 0 flag will be 1. So a flag is set when it is equal to 1. A flag is clear when it is equal to 0. Sign flag is set when the destination operand is negative. The flag is clear when the destination is positive. So here you can see move CX, 0 is moved to CX, 1 is moved, 1 is subtracted from the CX. So what will happen? We are subtracting 1 from 0, so CX will be -1 and sign flag will be 1, because it became negative. Here you can see we add 2, so it will be 1, it is positive, and it is being cleared right now. The sign flag is a copy of the destination's highest bit. You can see here 0 is here, move to AL. This is copy, means this is, if this bit changes here, it will be copied in the sign flag. If we subtract, initially AL is equal to all zeros, so but move doesn't change this sign flag. So all these bits, for example, just count whatsoever the number of bits are there, but it should be 8 bits. So 1 2 3 4 and 4 are 8 bits. So if we subtract all these bits, it will be negative value, and this one will be copied or in the sign flag. If we add, it will be, this will be the new value, and sign flag will show this one. So signed and unsigned integers, all CPU instructions operate exactly the same on signed and unsigned integers. It doesn't perform any different operation or different way to operate on signed and the unsigned. And CPU cannot distinguish between signed and unsigned integers. You, the programmers, you or the programmer are solely responsible for using the correct data type with each instruction. So be careful. As I told you, when you perform any operation, increment, decrement, if you want to perform move, you have to be very much careful. You have to observe the length. Just observe, observe the syntax of the instructions. You cannot perform move between two memory operands. You cannot perform move extend between two memory operands. You cannot perform addition or something, or move between two operands whose size doesn't match, and so on. Overflow and carry. So these are the two other flags. So overflow and carry flag. The how to add instruction modifies the overflow and carry. So overflow, carry out of the most significant bit. When the carry out of the most significant bit is exclusive OR with the carry inside the into the most significant bit. So it shows the overflow flag. And carry flag, carry out of the most significant bit. So carry out of MSB, exclusive OR with the carry into the most significant bit. It modifies the, it sets the overflow flag, or it modifies the value of the overflow flag. How the subtract instruction modifies overflow and carry flag? This is for the add instruction. How add modifies these two, and now how subtracts. Subtract modifies when carry out of the MSB and carry in the MSB, inside the MSB. So we exclusive OR. And what we do, we invert the MSB. Most significant means carry out of the inverse of the MSB, so we inverse. So most significant bit, and this is the exclusive OR operation and negate notation. So here you can see the carry flag is set when the result of the operation generate an unsigned value that is out of range, or too big or too small for the destination operand. AL is moved with FF, all these ones, and we add 1. So carry flag, AL will be 0, 0, and carry will be out. So if you just try to go below 0, what will happen? Again the carry flag is 1. If we AL is equal to 0, so in the previous slide you saw that there is an exclusive OR between the 8th bit and so on. Here this exercise, if we perform move AX comma 0, 0, FF, if we add, if we subtract and perform all these operations, what will be the value of AX, AL, AH, BH register and AL register, and what will be sign flag, 0 flag, and carry flag. So AX is equal to 0, 0, FF. If we add 1, what will happen? The value of AX will be 0, 1, 0, 0. Sign flag will be 0 because sign doesn't change, sign will remain same, carry flag will same, 0 flag will same. If we subtract, again there will be no effect. The result will be same as the previous value. Now we are going to perform some operation on AL. The value of AL right now here at this point is FF. So AL is equal to FF. If we add 1 to AL, it will be 0, 0. And definitely if it will be 0, 0, the whole AX will be 0, 0. So sign flag will be sign flag will be 0 because it doesn't affect the sign. 0 flag will be 0, and carry flag will be also set. The 0 flag and carry flag, they will be set. For the next one here, we have BH is equal to 6C and add BH with 9, 5 and hexadecimal. Now you can see the carry flag, definitely here the carry flag will be set. If you add this one and this one, the carry flag will be set, there will be 1 carry, and the new value is 0, 1 for the BH only. And sign flag doesn't change, sign is still the same as the previous one, because previously BH was value was 6, so 0, 1 1 0. So previously this bit, these 4 bits were like this one, and C was this one. So okay, so you can see this is the value, previous value, so it will not change anything, sign or the 0 flag. Now if you move 2 to AL and subtract 3 from AL, then the value in AL will be FF. SF sign flag will be definitely, it's minus. 0 flag is not, because the value is not 0, and carry flag is equal to 1. And overflow flag is set when the sign result of an operation is invalid or out of range. So here you can see AL has the most positive, the maximum positive value. If we add, then there's overflow, and we don't know what will be the value for AL. If 7F is AL, moved in the AL, and we add, AL will be 80 and overflow flag will be 1, so there's overflow inside the AL register. So what is the rule of thumb? When adding 2 integers, remember that overflow flag is set only when 2 positive operands are added and their sum is negative. One thing, 2 negative operands are added and their sum is positive. If 2 negative operands are added and their sum is positive, if 2 positive operands are added and their sum is negative, then overflow flag will be set, will become 1. This is one example, so we can see this example here. 80 is a hexadecimal, 80 and 92 is also hexadecimal, so we are adding 92 with the previous value of AL, that is 80. These are the two numbers, 2 negative numbers if we consider 8 bits. So what will happen? Overflow will be 1 because 2 numbers are added and the value is positive, and this one is negative, this one is positive. If we add them, definitely the value, previously it was negative and this one is positive, so if we add, it will be 125, so overflow flag will not change. Similarly, this is a drill question, that what will happen or what will be the values of overflow and sign flag if AL is the minimum value. Here AX is equal to the negative value, and if we add 2 in this one, what is the carry flag, overflow flag? If we move 0 to AX and if we subtract 2 from this AX, then what will happen? And similarly for these two. So if we move minimum value, minimum negative value, sign value to AL and perform negative sign, then carry flag will be 1, overflow flag will be 1, and similarly the answer for all these instructions. Now there is summary. We are going to summarize this one. In this lecture we discuss about the data transfer instruction, operand types, instruction operand notation, direct memory operands, move instruction, 0 and sign exchange, and direct offset instruction. And we also considered the add and subtract instruction. We saw about sign flag, carry flag, and 0 flag, and overflow flags for all these instructions. So this is the reference, and this is the end of the this lecture, and hope to see you inshallah in the next lecture. Till next lecture, Allah Hafiz.